today we're going to talk about deep reinforcement learning. Um, to reconfirm, can you hear me now?
Yep.
Yes.
Okay, thanks. Um, and so this is going to be our agenda for today. We start by reviewing some of the classical reinforcement learning methods that we covered in week 6. And then we kind of connect that to approximate reinforcement learning methods. So approximate reinforcement learning methods appeared a long time ago, maybe in late 1970s and 1980s, and then to early 2000s. And the main focus of these algorithms were not necessarily neural networks, but how to approximate the current ones, such as SARSA and Q-learning, with linear functions and very shallow neural networks. And then we'll talk about the recent developments in deep reinforcement learning, DQN, some enhancements on DQN, which was very revolutionary. We'll mention AlphaGo and AlphaGo Zero. We don't have enough time to cover the entire thing here, but we also talk about reinforced and policy gradient methods and how it's related to actor-critic algorithms, which are the state of the art at the moment, and they're doing a lot of cool stuff with them. Yeah. So yeah, let's start with the review of the classical reinforcement learning. Um, you remember that reinforcement learning was considered as a computational approach to learning from interaction, and it provides the formalism for intelligent and adaptive behavior. There were challenges along the way whenever you have these interactive learning paradigms. Actions have long-term consequences. We have delayed rewards, which is also known as the credit assignment problem. It might be better to sacrifice immediate rewards to gain more long-term rewards. You're also, we as intelligent creatures also aware of these challenges, and also the exploration and exploitation dilemma, which we try to balance that out with certain algorithms such as epsilon greedy and similar ones. I guess epsilon greedy will be the focus of our today's lecture too, and also practical, but clearly that's not the only available option. Um, so in reinforcement learning, we have three very important concepts: rewards, states, and actions. And so the state is basically provided by an environment, and actions is generated by an agent, and reward is also can be somewhere between the environment and the agent. But the fact is, whenever you have all these three elements, also called Markov decision process, you can formulate a solution with reinforcement learning algorithms. So notice that in in reinforcement learning, we have this structure of interaction between agent and environment. It's kind of a reference to how humans and other living creatures are dealing with that. It's pretty much like, responding and reacting to observations, and prioritizing the ones that are that will lead us to higher rewards. We talked about multi-arm bandit problems and how they can show us the strength of exploration methods to find the optimal policy. We also saw the general pattern of learning when we were studying multi-arm bandit problems, and this is like the archetype of learning in general. It's not limited to reinforcement learning or supervised learning, and the fact that we have an old estimate, it can be a classification or old classification, an old policy. We make some observations and we calculate some measure, a loss function, a difference, a distance, and then we have a step size, and we update our old estimate, we get to a new estimate, and we continue this iteratively until we converge to an optimal policy. So you remember the trajectory in a life of an agent. We can capture that with a sequence of states and actions and rewards. And when we write that like a sequence, it looks like this. And it's very important to have this notion because we use that to calculate our returns, which are very important in updating our agent. And this is again, we covered this in week 6, that in order to calculate the return, you can either directly sum all the discounted rewards, or you can use this recursive notation to calculate it. And this is the basis for the TD methods, SARSA, and Q-learning. Markov decision process. So we remember that it introduces assumptions to deal with reinforcement learning at a mathematical level. There were some important assumptions about this called Markov property, and the fact that all you need to know is already here. You don't need to look back and study previous and prior states. So this is a very questionable thing when we get to approximate reinforcement learning and deep reinforcement learning, because it in certain environments, certain situations, you actually need to look back. But to counter that and to keep the Markov property, you will see that we modify the state to include all the necessary information now. So that's one possibility. The other possibility that I will mention later is that we will augment our agent with some sort of embedded memory. So yeah, the agent doesn't really need to go back and look at the states in the past, but it has the necessary, it registered the past somehow, that it can look, without looking back, it can access those states. So one possible solution is using LSTMs, for instance, or RNNs, that they kind of capture temporal patterns, and the agent can incorporate them into its decision making. Anyway, and this is also another thing that we mentioned, and you'll see how this actually works out today. That almost all RL problems can be formulated as MDP. So again, to reiterate, whenever we have state action, a transition probability or dynamic, or and a reward, you can formulate that problem with you can formulate it with MTB when you have all these components, and when all these components are available, you can solve it with a model-based or model-free reinforcement learning algorithm. And you will see one application of that today for image captioning and text generation. We will apply reinforcement learning, and the way we do that is that we find these elements, and once we find them, then you can solve it with a reinforcement learning algorithm. So you remember the concept of policy. A policy is the thing that we're after, and it basically maps this state to the action or a probability over actions. And especially when you're dealing with stochastic policies, when it's deterministic, you don't see the P here. It's basically mapping from S to A. But in stochastic ones, it's just a probability. And so the solution to an MDP, you remember that is a policy. This is, again, this is what we're after. In many cases, you can't really directly access this policy, this function here. So instead of using, directly using a policy, we define the notion of a value function. And so, as I mentioned, a value function was like an advisor, and you ask for the highest value, or you ask about the value of this particular state. I will tell you the value of that. So it's not necessarily accurate, But iteratively we update that, and you know, little by little it gets better and better, and it, you know, makes better predictions, and we use that as a proxy for our policy. And almost all of the algorithms that we covered by now, and most of today, are value based reinforcement learning algorithms. We also mentioned reinforce and some policy gradient algorithms that are purely policy based. And we also have, um, as you remember, we had two types of value functions. One of them was state value function V of an MDP, and the other one was action value function. So the good thing about action value functions were that we can directly utilize them um, to create reinforcement learning algorithms, and SARSA, Q-learning, and DQN, which is the topic of our today lessons, is they're directly using Q functions, and you give it a state and action, it will give you a value for that. And whenever I'm in a state, I calculate the value of all the possible actions in that particular state, and I compare them. And if I want to act greedily, I choose the maximum one, and easy. And if I want to explore, I can use epsilon greedy. So with a certain probability, I'll act randomly, and you know, in other cases, I'll act greedily. And this will help me to our agent to actually converge to an optimal policy eventually. The state value functions are trickier because you can't directly use them to find a policy. But the good thing about value functions is that they can evaluate a policy for you. So let's say you have a policy and you want to see how good it is, right? So you generate a value function for that. And this is actually, these value functions are also used as critics in actor critic algorithms. So there is a policy, and these guys, they're kind of standing over the policy and giving the policy feedback about its decisions, and they both learn in this way. And we'll talk about this further. All right. So introduction to approximate reinforcement learning, guys. Is there any question by far?
No, like,
okay, thank you.
It seems mostly in line with what you talked about last time.
Yeah, exactly. Thank you. So introduction to approximate reinforcement learning. So model-free reinforcement learning algorithms such as SARSA and Q-learning that we discussed before, they can, you know, they're great. They can find optimal policy for arbitrary environments. You don't even need to know the model or the probability transition of that environment. Just give it the environment, it'll find the optimal policy for you. But there is one huge assumption here, or huge if, that if the value functions and policy can be represented in a table of values, right? And this can be very problematic because most problems, most real problems, are too large and too complex that you can't, you know, represent them in a table of values. In some cases, it's not even discrete. So a table is a, you know, there must be states. There must be ways that you can say that this is this state and it's distinguished from the other one. But in reality, in many situations, the state itself has a lot of continuous values, and so you can't directly represent that in a table. The only way that you can do is to discretize or make it discrete, and which comes with its own problems. But even in discrete environments such as board games like chess and Go, um, these guys are, you know, they have ginormous amount of states. So it's uh, postulated that Go itself has 2 times 10 to 1/17 legal states, which is the square of the number of particles in the visible universe. And well, clearly you can't save this amount of, and notice that this is just a number of legal states. If you want to save the Q function for this, you need to multiply this by the number of possible actions in each legal state. So it's impossible to save this in a table of values. So what other possibilities do we have? So one possible solution is using functional approximations and or machine learning methods that we covered by far. And so someone might ask us why these methods are helpful. Why can we solve them with machine learning methods, and how they're actually solving this curse of dimensionality? Um, and the answer is easy. Machine learning algorithms are good at generalization, and so you throw millions of data points at a classification or regression function, and it comes up with a line or a curve that classify them or separate them or predict their behaviors, and it kind of liberates us about from thinking of individual data points. Um, and that's exactly how this works, that we approximate. And by approximation, we are finding some general patterns in our data, and find similarities and differences between states. And this can also be one of the problems with functional approximation methods, because once you update your network, you're not necessarily updating one state and action, you're updating multiple states and actions. And if we don't, yeah, if you use a very bad method, your model actually may never really converge. So the next question is that, will reinforcement learning work with functional approximators? And this is the thing that we're going to talk about later. We can represent the state value or action value function by a parameterized function approximator. And this is how we change the notation. So you remember that in tabular methods, Q of SNA was represented with this. And now we add this theta here, or W, it can be theta or W, doesn't matter. It just represents the weights of our linear function or our neural network. In case of a state value function, we turn that into this notation. So whenever you see something like this, or V of S or W, or Q of S and A or W, or something like that, doesn't matter. Whenever you see this notation, it means that we parameterize these functions with some function approximation method, such as a neural network or a linear function. So as I mentioned, function approximations such as neural network addresses two of the problems in tabular methods: the curse of dimensionality and the lack of generalization. So again, in tabular methods, whenever you update your table, you're updating one particular state and action in Q function, or at least in state value function, we're updating one state. But in the neural networks, you're updating multiple of them in one move. So it's great. All the recent success stories in reinforcement learning are coming from the power of approximators. But the thing is, it also suffers from one theoretical problem. There is no guarantee for their convergence. So if you go back to the history of reinforcement learning, there was an urge to find or to prove that a certain method will converge. And in early papers on reinforcement learning, there were a lot of mathematical proofs of why a certain method works and why it's converging, and it must converge because of these and that reasons. In functional approximation, we usually don't have the guarantee, but interestingly, these methods that don't have the guarantees, they actually converge much better in much more complex environments. All right, so let's convert the SARSA algorithm to its function approximation counterpart. So you remember this method, the SARSA, this is the tabular SARSA method. It's a unpolicy TD control. And you remember that this is the MDP loop. And in the beginning of each episode, we initialize the state. We take the action for that state using epsilon greedy, and we go to the game loop here. We take that action and observe the reward on the next state. And yeah, so we take the next action and we update our Q function. And that was pretty much the entire algorithm. And we also implemented this. So the main beef in this algorithm was this update formula here. I mean, you can clearly you can keep the rest of the algorithm, and we need to somehow come up with a solution to convert this to a approximate method, right? So before moving to the actual algorithm, let us talk about the error here. So notice that we have this expression, and this is the TD error, right? So we use this TD error as a way of dealing with a function approximation. We turn this into a loss function, right? So consider the following objective function, mean squared error based on the Bellman equation. Imagine that you're dealing with a regression problem, right? In a regression problem, where the loss function is MSE, right? Which is the expected. So we average over, so we have a label, not necessarily label, but let me delete this. So we predict something, and we subtract that from the actual value. And we calculate the square root of all of this. And this was the mean squared error algorithm. And we are turning the TD error into the exact same thing. So this will be the target, the actual value, and this is our predicted value. Now, you may say that, well, that's not actually true, because this is actually coming from the same function. This is exactly this function. How is this even possible? Yeah, and that's why this is not a fully gradient algorithm. It's actually called semi-gradient SARSA, because it's we're assuming that this function here is not dependent on W, on the thing that it parameterizes it with. So the target here, this expression, depends on the parameter, but we ignore that dependence when thinking, when taking the derivative. Then we get this, as a result of taking the gradient from this, we get to this formula here, right? So if actually, if I calculate the gradient of this, if I actually take the gradient of this, it will be like -2 gradient of Q, S, A, and W with respect to W, and then the entire TD error, right? And this -2 is usually absorbed by alpha whenever we're calculated. And there we have our update rule. And that's our first function approximation method. And this is the algorithm. And as you can see, it's almost identical to the tabular SARSA. The only thing that is different is the update rule. And they also added this if this is terminal, but we kind of handled that when we were implementing the tabular SARSA, so it's not a big deal. It's just saying that when the next state is um, terminal, just remember to remove this expression. If not, then consider it for calculating um, the gradient. All right, guys, is there any question about this?
No. Like I'm a bit rusty on like the math, so I'm not too sure about that. But the general sense of stuff, yeah, I think I'm understand.
Right. So this notation here is also very similar to, well, it's not similar, it's exactly the gradient descent. This thing here is the gradient descent, and we literally use this in all machine learning algorithms.
Oh yeah. I meant specifically like when you were talking about like
oh yeah, the
like
taking the gradient.
Yeah, the what was it? You derive.
Yes.
Yeah, that stuff. Yeah.
Yes.
Like I'm pretty rusty when it comes to that. Yeah.
Yeah, that's okay. I was just explaining that how this formula came into being, and once we have the formula, you can't forget about the math. So once you calculate this, then you can implement this algorithm itself, right?
Right. Yeah.
All right. So what are the problems? Function approximations idea is that we combine neural networks with reinforcement learning, and there we have intelligence. And it's usually not that simple. Sometimes, but with deeper neural networks and more complex environments, these methods may actually diverge, or they sometimes forget after learning something, and which is this phenomenon is called catastrophic forgetting, especially when you combine neural networks with Q-learning. So you notice this algorithm. This is SARSA, right? So if you do the same thing with Q-learning and turn the tabular Q-learning into a approximate Q-learning, I actually did that, and you will see a reward that you see, and if you plot the rewards that your agent gets, it looks like this. So it learns, so for a couple of hundreds of episodes, it learns nothing, which is usually normal, and it suddenly learns something, and it gets to a very good point here, and then it suddenly crashes. And again, it learns something here, it crashes. And this continues forever. Your agent never really learns this thing. And it's usually due to a categorization that is known as the deadly triad. So the deadly triad says that if you want to use function approximation on a method, just make sure to avoid these three together. If your model, if your algorithm has all these three methods, it's very likely that it's going to be unstable and actually diverge. So function approximation, a neural network or a linear model, bootstrapping, so all TD methods like SARSA and Q-learning are using bootstrapping, and also off-policy training. So Q-learning is off policy. So Q-learning if you parameterize Q-learning with a neural network, it has all these three components, and hence it diverges. So for SARSA, we're using function approximation and we're using bootstrapping, but it's on policy. So one component is missing, and that's why it works, right? So be aware of the deadly triad. Now we can solve the deadly triad with some extra with introducing some extra components, which is the topic of our DQN method. So yeah, we saw that Q-learning had a lot of strength in tabular form. Yeah, this is, I guess I already covered that. Unfortunately, when we apply approximation methods on Q-learning, it diverges, as I explained. And all right, so we mentioned that if you see deadly triad, your model will be unstable. We didn't give you, we didn't really provide a reason for this behavior. And when actually some people studied this, they realized that there are at least 3 reasons for that, especially in the case of Q-learning. So the problem is that there are correlations in sequence of observations. So when you observe something and you do something, it's highly correlated with your next state and next actions. So you're kind of narrowing down your decision making as you're making your decisions. And the problem is that you're updating your network with the trajectory that you're generating from your network itself. And this leads to to a high correlation data, especially when you're dealing with the gradient descent algorithm. One very important assumption of gradient descent algorithm is IID, or the fact that data must be independent and identically distributed, which is violated in this example. Small updates to Q may significantly change the policy and therefore change the data distribution, one of the problems of function approximators in general. And also another correlation, the correlation between the action value and the target values. So all these correlations and problems can lead to and snowball to the diverging, or at least an unstable agent. It may converge from time to time, but the problem is that there is no guarantee for that. Now, in DQN, the Deep Q network, they addressed all these 3 issues by introducing 2 revolutionary concepts. One of them is that experience replay buffer, the thing that I'll elaborate further, and you're gonna also implement it in today's practical. And a target network, which is a copy of your network, but with a delay, and it will solve some correlations. The third correlation, the correlation between action values and the target value. Now, before starting, so now we're stepping into the depth of deep reinforcement learning. Before talking about DQN, which is our first algorithm, I'm just gonna talk about some of the recent advancements in reinforcement learning, which were really awesome to the world, and it was published on BBC, and people made documentaries out of them, and they also ignited a lot of talk about singularity and things like that. So I think the first one, which came into public, understanding about reinforcement learning, was the DQN paper. So know that we have 2 versions of DQN paper. One was published in 2013. In the 2013 version, they only covered experience replay buffer. In 2015, they published a second paper, and they also considered target networks. Now, this second one was published in Nature, and created a lot of buzz. And but the revolutionary thing about DQN, especially DQN 2015, was that they gave the pixel of all the Atari 2600 games to the DQN agent separately. It's not just one agent, so they retrained one algorithm for each environment, and in all of them, the agent actually learned, and it got really good. Sometimes even it got better than a human expert, and that's why the name of the paper is human level control through deep reinforcement learning. Yeah, so that was the DQN algorithm. The second paper and the second work that really shook the world was the AlphaGo and AlphaGo Zero paper and competition. So you may have heard of the AlphaGo and AlphaGo Zero agents and the game. There's also this documentary by DeepMind about the entire challenge and then people involved. Some of the scientists, such as David Silver, who is the lead scientist in DeepMind, and they explain how the agent actually works. So in 2016, they proposed AlphaGo, which used human data as demonstration, and used imitation learning to learn from human data. But later in 2017, they kind of get rid of the imitation learning part and came up with a revolutionary algorithm called AlphaGo Zero. It learns directly, from the game. It has, a very deep neural network, some reinforcement learning, and Monte Carlo tree search, which is a stochastic tree search. Normally, whenever you're playing a board game, you need a tree search, and CTS or Monte Carlo tree search is the most popular ones, especially these very large game trees, and also a self-play mechanism. So the agent was playing against itself, and in doing that, it was trying to defeat itself, and it was like a bootstrapping architecture. It was getting better and better at defeating itself, which was making itself better. And in each iteration, it learns how to come up with some new mechanisms to defeat itself. And after, I guess, 3 weeks of training, it got to the super level human, and eventually in 2017, it beat Lee Sedol from South Korea, who was the grandmaster of the game of Go. And I guess he even quit playing Go after that defeat. And yeah, the third, maybe the final achievement was Alpha Star, and again there is a 5-minute documentary on that. I also provided a link on iLearn, which you can watch this. It's not as flashy as AlphaGo and DQN. I mean, there are people in game community who are familiar with um, the Alpha Star and the game itself. But other than that, people are not interested in this game much, and that's why it didn't really make so much buzz compared to AlphaGo. But they trained a bunch of agents to play this multi-agent, multiplayer game. They used Impala for that, which is the state-of-the-art algorithm, and they used an astronomical amounts of computational power. I think I heard somewhere that they trained each agent for the equivalent of 10,000 years of human training. So they threw tremendous amount of computational power at this, and to show that it's actually successful in these. Yeah, so these examples are showing how successful it is. And I guess the good thing about video games is that it will give you a very cheap environment to just test the algorithm itself. Now, if you want to do the same thing in robotics, it's going to take you a lot of resources. But video games are easier, and we're also shifting from this understanding of directly training robots to training the equivalent, the kind of simulated version of those robots, and then transferring the brain of those agents into the actual robot. And this is pretty much the way that people are approaching robotics nowadays. So in the past, in 1980s and 1970s, they were just training the robot from scratch by a new reinforcement learning algorithm. Now you're getting this, that it's not possible to do that. It's very expensive to do that. So let's come up with a simulation for our agent and then train that in that simulation, then transfer it to the actual robot. Now let's talk about DQN. So first of all, it's very similar to the approximate SARSA. We just add two components to that, the experience replay buffer and the target network. An experience replay buffer is like pretty much like a data set in a supervised learning, and the experience replay buffer is actually helping the Q-learning to become like a supervised learning algorithm, which I'll explain more just in a minute. And the difference is that the agent, so in supervised learning, the data set is provided from outside. In reinforcement learning, in DQN, the agent actually collects this as it explores the environment. Now, in every step, the agent adds its experience, which is a tuple of state action, new state reward, and done signal. This whole thing is called an experience. They add it to the data set, and in every d time steps of the life of our agent, let's say in each four steps, we, like a supervised learning algorithm, we sample from this data set, the experience replay buffer, and train our Q functions network with it, like a normal regression. So the second kind of revolutionary idea was the target network. So a target network is a copy of the main network with a delay. It's mainly used in the calculation of the target. So you remember that the target was R plus gamma Q SNA, right? So this whole thing was target minus Q SNA, right? And maybe you should say this was, oh, sorry. This was SARSA. If you want to use Q-learning on that, you should also add a maximum to this, but it doesn't matter. The thing is, the target is used to calculate this. And the delay, so you remember that when we were taking the derivative or the gradient of this, we had to assume that this doesn't depend on the parameters of the network, which is not very strong. To make it better, we can use the target network to calculate this. And that delay actually guarantees that assumption. And this is the entire algorithm. So it might appear a little daunting and overwhelming, but it's actually very easy to understand. So let's start from the beginning. We initialize a replay memory. It's a data set, right? Nothing really fancy, just a data set. And we initialize action value function Q. It's a neural network. If you're implementing it with TensorFlow and Keras, you create a sequential and just stack up some layers. And a target, which is a copy of the same exact network. You basically initialize the two networks. That's it. And then this is the MDP loop. You're familiar with the MDP loop. In each, so we initialize our environment, and we preprocess the sequence. I'll talk about the preprocessing of the sequence because the main prospect of DQN was dealing with pixel games. And because of that, you need to modify the image a little bit, make it square, make it grayscale, and shrink it down, things like that. So that's the pre-processing. Also, frame stacking, which I'll explain later. But if you're dealing with a vector environment, a very simple one, a classic control one like the cart pole or mountain car, the things that we're going to deal today, you don't need to do this. It's just the state itself. Now you take the action with the epsilon greedy. You remember epsilon greedy. And right. So instead of, so you remember in SARSA, we use the Q function and everything to directly update our function. Now, once you take the action in a particular state, you observe the reward and the next state. Instead of updating your network, you just save it, right? You pack it up in a tuple, like this. You also may want to add done because you need it for update, but that's the general idea. You save the experience in your data set. And then you sample from that data set randomly and update your network with the mean squared error, like a normal regression function. And that's it. That's the entire algorithm. And that actually solved a very serious problem in deep reinforcement learning. So you can say that DQN is actually reinforcement learning plus the power of supervised learning. Guys, is there any question about this? All good?
Yeah.
All right, thank you. All right, let's talk about the preprocessing function that we mentioned. So the main target of DQN, as I mentioned, was learning from pixels. This requires some image processing before giving the image to convolutional neural networks. And so what do we mean by preprocessing function? Cutting redundant borders, such as getting rid of these numbers here because they're not part of the game. Again, these borders here, they all must be cut off. And when possible, make image grayscale. In certain games, such as this pond here, you don't need to see the colors. Sometimes you do, but in most cases you don't. So you make it grayscale and easier for the agent to process it. You make it smaller and square instead of, so at the moment it's not perfectly square. We make it completely a square and make it like I don't know, maybe 84 by 84. I think that was the original size in the DQN paper. And also another thing that is called frame stacking. So notice that if I show you this image here and ask you what should we do, you can't really say because the only thing that you can see is that where you are and where the ball is. Now let's imagine that you don't have a memory and you forget. So if I show you the next image and the ball has moved and you don't know what was the previous image, it is still the same situation. You don't know how to respond to that kind of question. To solve that problem and to make it more Markovian, so to speak, or to keep the Markov property assumption, we do this thing that is called frame stacking. And it's demonstrated here. Notice that in this example, so the red colors are, this is the beginning state and that's the end state. It means that it just shows the trajectory of the ball and the trajectory of, or the place of the agent. So by doing this, and the agent sees 4 recent frames of the game, and by doing this, we'll make this Markovian and preprocess it with our convolutional neural network. and this actually helps the agent to converge. If you don't do this, the agent never converges because it can only see one state at a time, one frame, not one state, one frame of the game at a time, which is not Markovian. So another possibility for that is to augment our agent with recurrent neural networks, which is a kind of a memory or even attentions. It makes it much better because then the agent knows where to focus on the image and things like that. But if you don't want to use RNNs and memories and things like that, you just use frame stacking, and that was the method they used in the original DQN paper. So again, note in the practical, you use the classic control environments such as mountain car or cart pool. The state in these environments is a small vector. So cart pool, for instance, has two variables. One of them is the position of the cart, and the other one is the angle of the pole with the cart, and that's it. And we don't need to pre-process it in this way. We're not processing pixels. Now, when learning from pixels, we should follow a CNN architecture like this figure. In vector environments, we just used a multi-layer perceptron, just one or two dense layers, and that's it. But this is the architecture they used in the original DQN paper. So you can see that we have the stacked image here, 3 conv layers, and with different number of filters. Started with 32, then 64, another 64. Kernels are changing, and strides. We started from a stride 4x4, and then get to 2x2, and then 1x1. And then finally, we have, after flattening here, we have 512 units in our first dense layer, and then the ReLU activation, I believe it was ReLU activation, and also the final layer was also the number of actions, and yeah, and that's how this network was organized. Now the question is that, can we make this algorithm even better? Yes, there are many possibilities for that. For instance, there's this concept of double DQN. So it's a known problem that DQN or Q learning are over optimistic. So you can solve that with a method called double DQN. If you remember, I kind of mentioned this in week 6 that we have double Q learning. So this is the deep version of that. Dueling DQN, so making a DQN more robust by breaking down the Q function at the neural network level. So notice the years, this came in 2015 and then 2016. Priority experience replay buffer, very important concept. This is also true about humans. So we also do experience replays. There are actually biological reasons for this concept that they used. It's also observed in rodents or even humans. When we sleep, we and you have dreams, that's some sort of experience replay. Or when you flashback or you remember something when you're making a decision, that's some sort of experience replay buffer. Now the thing is, you don't remember everything equally. So there are things that are more important and there are things that are trivial. So it's the idea of priority experience replays that all experiences are not equally important. By giving more weight to more important experiences, we can speed up training, and it actually helps the agent to converge faster. And then in 2017, they put them all together and make like a super DQN algorithm. They even introduced some extra ideas such as noisy networks for better exploration, and n-step bootstrapping, which I'll mention later today. Let's start talking about policy gradient methods. So far we have focused on value-based methods such as SARSA and Q-learning before, which we saw that it's not very feasible to use function approximators um, with the Q-learning itself, but we augment Q-learning with target network and experience replay buffer, and then came up with DQN. But all of these are value-based methods, which means that decision-making process in approximate value methods, this is pretty much the way we do it. The state is processed by a neural network, the Q function, the Q values for each action and action policies, epsilon greedy, will generate an action in each step, and we update the Q function, but the goal is to do better or a better policy. So we're always going around a value function and then find the policy after this. The question that many people asked a long time ago was that can we do this? Can we do this directly? Is it possible? I mean, it was very obvious when you were dealing with tabular methods that it's not very obvious how to do that. But once we start using function approximators such as neural networks, is it possible to do that? And the answer was yes. And this is pretty much the structure of this, that we provided the state and we gave it to our network. And the output was a probability distribution over actions. Um, so policy gradient methods, or the methods that directly parameterize the policy itself, they're also good at one thing that Q-learning and SARSA and all of them were suffering from, the problem of dealing with continuous action spaces. So notice that whenever you're training a DQN or SARSA, the output is, so let's say we have two possible actions. So one action is left, the other action is right. For a very simple environment such as cart pull, right? So we have a neural network, and then they kind of generate these outputs, doesn't matter. So it's left or right. When you're dealing with a discrete action, so when it's either left or right and there is no magnitude to left and right, then using DQN and SARSA, approximate SARSA or DQN would be feasible. Now, let's imagine that choosing the action is not the only thing. You also need to know the magnitude of left or right. So let's say you can choose a value between -1, between 0 and 1 for left, and 0 and 1 for right. And these are actually part of the real numbers. So it can be left for 0.2 or 0.5, and they're actually different. So when you're dealing with these kind of environments, it's almost impossible to use DQN and SARSA on them. And to solve that problem, policy gradient algorithms are great, and that's exactly one of the reasons we're talking about them, and that's why they're important. The other thing is that it's not necessarily a continuous action space. Sometimes a very large action space can be a problem. So let's say you have 10,000 possible actions, right? They are still discrete, but there's so much that you can't possibly put 10,000 outputs to your network in a DQN. And that's why we prefer a policy gradient algorithm. And so in image captioning and text generation, this is one of the reasons that we're going to use reinforced, that I'll talk later. Okay, so what is a policy? As a review, a stochastic policy is a function that maps states to action probabilities, which is used to sample an action from. And what is a good policy? Like all reinforcement learning algorithms or methods, the objective is to maximize the cumulative discounted reward, or G. So you remember this from week 6. The objective is the expected return over the entire trajectory generated by the agent. So this is the objective, and we're trying to maximize this objective. So the more reward you collect during a trajectory or in an episode, the better. So that's the general idea. As you remember, that's the general goal of all reinforcement learning methods. And so um, to maximize the objective, we perform gradient ascent on the policy parameters. Um, and But there's one problem here, that the return or g of a trajectory is not differentiable with respect to theta, right? So theta are the parameters of the network, and there is no way that you can take the gradient of the expected cumulative rewards. So the solution is to transform the objective function to a differentiable format, right? And the other reason for, I'll talk about this later, but the other reason for non-differentiability is that the rewards are coming from an unknown function. It's not dependent on theta, which are the parameters of our network. And that's why if you take the gradient from them, it's going to make them zero. So you can't do this directly to the cumulative reward, but you can do some mathematical gymnastics and find a possible solution for that. So there are some math here, which it's not necessary again to go over all of them and understand them line by line. But if you remember calculus or some kind of late high school math, um, you may actually find them interesting, that how they transform the cumulative reward into a differentiable function that we can use for our first policy gradient algorithm, which is called reinforce. Um, I just briefly explain how things are going, how things are happening here, and how we're transforming them into the differentiable format. But I'll just skim through them very quickly. So given f, it's not necessarily something reinforcement learning related. Just assume that we have a function called f. It's parameterized by probability distribution p of x given theta, which are the are given parameters, and then we're trying to take the gradient of this. Clearly, it's not directly possible. So imagine that f is a continuous function. If you use the integration of the definition of the expectation, you get this. You distribute the gradient inside, and here we have the product rule. Product rule from calculus, and this gradient will be zero because f of x is not dependent on theta. This is the remaining one. We do some extra mathematical gymnastics. It's called the derivative trick, and you know that the derivative of log of something like p of x can be written as this. So remember that d of log of x was 1 over x, right, from calculus. So this is pretty much related to that idea. And yeah, that's the final output. So the gradient of the expected of a function will be the expectation of f of x gradient of log of probability, right? And so we can use this exact same thing to write our objective function this way. So the gradient of the expected cumulative reward can be written as this, which is, so this is the g, and this is the gradient of probability. It is still soon to use this. We need some extra steps, which means that the probability of a trajectory can be written as the product of the probability of our decision making times the probability from the environment. So in a nutshell, this says that the probability of a trajectory happening depends on two things, the way you make your decisions and the way the environment reacts to it, right? It's also aligned with our common understanding of the world. It's not entirely up to you or the environment. It's a mixture of both. Um, Now, if I take the log from this product, you remember that the log of a product is you return that it turns that into a sum of log of probability and log of policy. Now, if I take you remember from this page that we are interested in log of in the gradient of this log. So the gradient of this will make this probability 0 because it's not dependent on theta. And here we have the final um, formula. And this is actually the holy grail of this whole policy gradient method. Um, we can directly turn this into an algorithm, and that algorithm is called reinforce. It's very important. Almost all actor-critic algorithms are, they're using this formula. All right. So again, we can turn that formula, update formula, to the simplest policy gradient algorithm known as vanilla policy gradient or reinforce. And reinforce is a Monte Carlo algorithm, right? So you remember that we had this, you know, what was called? We had a Monte Carlo algorithm in week 6. It was first visit. Yeah, it was first visit on policy Monte Carlo algorithm. And this is very similar to that because it's Monte Carlo. And the way it's done is that you go through an entire episode and use that policy to generate a trajectory. And it's not very clear here, but usually you go in backward in reverse and calculate all the returns, and then use that return and the gradient of our log of probability to update our network. And that's it. That's the entire algorithm. Um, all right, guys. After this, I need to go and talk about reinforce with baseline. Just want to make sure that you understood at least somewhat to this point. Do you have any questions, any confusions?
No, I kind of got a bit lost on the math specifics, but I think I get the general idea.
Right. So don't worry about the math too much. I was just trying to say that so in many books and many, because sometimes when you're learning about reinforcement learning and the policy gradient algorithms, actor critics, they just show you this final formula, and it can be difficult for people to understand how it came into being. I know that the math is not, so you're not supposed to understand the whole thing in just one glance and in one setting, but to know that there was a reason for its existence, I think it's easier to relate to, and that's why I explain it very quickly. um, but the point is not the math. The point is to know this method itself. Yeah.
Okay, yeah.
Yeah. And one possible question that some people may ask is that how are we going to actually calculate the gradient of log of probability of this policy? And well, it can be a little tricky to actually implement it in certain libraries. But at least in TensorFlow or these modern deep learning libraries such as TensorFlow or Keras or PyTorch, whenever you're implementing such a thing, so this is very clear. This is just like an accumulation of rewards, so just sum of rewards, right? Nothing cryptic here. Now, this part is interesting because you have your network. So let's say you have your neural network here, and it generates, let's say, a couple of outputs, let's say 2 outputs. And the output of this network, we usually call them legits, right? Before processing it with anything like softmax or anything like that. So the way we do this is that we give these logits to a probability, to a yeah, to a probability distribution such as categorical, right, or something like that, or normal distribution, depending on the type of actions we're dealing with. And this will create a probability distribution over actions, right? And then we can sample from this, and it's usually called the sample function. And they also, these functions, you can also implement them yourself, but it's easier to use the prepared ones. And then you can also, they all have this log prop function. And so this creates the action, and this action can be given to the log prop, and that's how you calculate the log prop. And you keep, so when you're generating your trajectory, you collect two things. I mean, like, not exactly two things, but the trajectory itself, which consists of state, action, and reward. You also collect the log probabilities. And when you're calculating it, you use the collected log probabilities and the information from this trajectory, which lead to this G, to update your network. Yeah, so that's the secret behind calculating this in real world. But doing this is not part of our practical today. If you're interested, you can go ahead and try to implement it yourself. It is also compatible with some simple environments such as cartpole that we're going to tackle with DQN today. So you remember that Monte Carlo algorithms were suffering from high variance, and we also dealt with that when we were comparing Monte Carlo, tabular Monte Carlo with SARSA and Q-learning, and you saw in tabular methods, SARSA and Q-learning overtook Monte Carlo because of the high variance in Monte Carlo methods. Now since the original reinforce is also Monte Carlo, it also suffers from the same thing. Now, the first step to counter this is to introduce a baseline. Now, it turns out that if you subtract an arbitrary value, it can be an arbitrary value, or it can be something that you derive from the state, like the state action function, right? If you subtract something from your return, it actually lessens or reduces the variance in your formula. But at the same time, as you can see here, it doesn't influence the gradient of that. So it means that it's not going to change the course of learning, but it reduces the variance, which stabilizes learning, right? So you're not going to see so many wiggly rewards when you're adding a baseline to it compared to a purely Monte Carlo method. And yeah, so you change the update rule to something like this, and this is a reinforce with baseline, and as you can see, so the original reinforce only had this part. We also introduced delta here, and delta represents the TD error, right? So in each step, when you're calculating the return, you subtract that from the value of a state, and you update the value, the parameters of the value function and the parameters of the policy at the same time. Right? And this is the closest thing to actor-critic algorithms. It is still not an actor-critic algorithm because the value function is actually functions um, like a baseline. It's not actually informing the policy about the right trajectory and its performance. But it's one step closer to the actor-critic algorithms, which I'll talk after our example. So so that was basically the reinforce and the reinforce with baseline. So let's talk about one recent application of this outside reinforcement learning. Oh, if I can. Sorry. So reinforcement learning can act as a tool for text generation. So GANs, generative adversarial networks, reinforcement learning, attention, and transformers are all state-of-the-art methods in this field. Mark will talk more on this on week 13, but one of the applications of reinforce and the reinforced algorithm and reinforcement learning was text generation, and this is one of the examples of that. They turn an image captioning problem or text generation problem to reinforcement learning. So you can see that this is the generated caption by human, and this is something that was generated by an attention network RNN with CIDR feedback. I'll talk about CIDR and other NLP metrics in a few minutes, and then this is like from that paper that I'm borrowing this image from. That you can see that the human says a large jetliner taking off from an airport runway, and this one says a large airplane is flying in the sky, not very accurate. So another one says a large airplane taking off from runway, and the same thing goes. You can see that it's kind of comparable to what a human would say, and this is also true about the next image. And they're using reinforcement learning as part of their algorithm, as I'll explain. So in image captioning and text generation, this is the method that we usually use. That we use cross entropy method to maximize the probability of the observed sequence according to the model. So we have a loss function, and the loss function is this, and we're trying to maximize the likelihood of the generated text, right? So this method clearly has limitations because it's only objective. The only objective of this method is to find the most likely sequence of words. It's not caring so much about the actual meaning and many other factors. It is still a very successful method, but we can do better. And to do that is to augment this method. If we're not getting rid of it, we're going to augment this method with some reinforcement learning. And this is how it works. We first pre-train our RNN or neural network with the cross entropy method for, say, a couple of thousands of iterations. And it usually hits a plateau of performance. And once that happens, we try to implement, we try to train it, continue our training with reinforcement learning. Now, to do that, you remember that we need to turn the problem into Markov decision problem, which means that we need to identify the state, action, the environment, and its dynamic, and a reward function. And in this case, this is how we approach it. The recurrent neural network, the network itself which is a generative model, is going to be our agent. The agent or the network does actions in the environment. And in our case, actions are going to be generated words, and the environment is the context vector. So when you embed your text or maybe preprocess your image, the final thing before generating a text is called a context vector. So that acts like an environment. And what about the reward? So one way is to give each generated sequence to humans for assessment. It's possible, but the problem is that humans are expensive and they make a lot of mistakes. So a long time ago, people in NLP came up with a lot of NLP metrics, such as blue or rouge 2 or cider, as you saw in the previous slide, and many other. Spice is one of them, or meteor, and they're used in different areas for data summarization, text summarization, translation, and so on. So these metrics can act like rewards for our agent or the RNN generative model. The fact is that the reason we're augmenting this method and we're keeping it and then later kind of retrain it with reinforce is that reinforce struggles to bootstrap the model. So we start training with cross entropy, then refine the model with the reinforcement learning algorithm. There are some relevant papers on that. The first one that came up with the idea was Mixer, and then self-critical sequence training, I believe. They all focused on image captioning. Mixer was more general. They talk about translation, machine translation, and also image captioning and so many others. But I think SCST was focused on image captioning. Yeah, and you can see that this is the algorithm. It's not very complex to understand. It just says that we're gonna, so if it's only cross entropy, we entirely train it with cross entropy. Otherwise, we're gonna train our RNN with this number of epochs with cross entropy, and then we switch to reinforce and we train it for this amount of steps with reinforce. And yeah, it led to a good result in some of the recent works. So our final topic for today is actor-critic algorithms. There are a lot of things that I wanted to cover, but unfortunately we don't have enough time or space to cover them. So I'll just show you the simplest possible actor-critic algorithms and then talk about some of the new advancements in this area. So the actor-critic algorithms are very related to reinforce and reinforce with baseline with some extra modifications. So the reinforce algorithm with the baseline sets the stage for actor-critics. Although reinforced with baseline can learn both policy and state value function, the state function is still a baseline, as I mentioned. A critic usually uses bootstrapping, like TD method. So the reinforced was Monte Carlo, and reinforced with baseline was also a Monte Carlo algorithm. To make it, like a real critic, one condition is the critic to be a TD method, so it bootstraps and it directly influences policy learning. And this is the simplest actor-critic algorithm imaginable from the Sutton's book. And as you can see, after taking, this is not a Monte Carlo algorithm. It's actually on policy, and in each step we take the action, and after observing the next state and reward, this is the TD error, like the baseline in our reinforce, and right after that we update both networks. This is the critic, and this is the policy, right, or the actor. So this is the policy, and this is also the value function of V of S. And yeah, as you can see, but delta here is using the values from the critic itself. So that's how the critic is actually influencing the policy. So remember in reinforce, we were just using G, the return, and then the gradient of log of policy. So we replace that G, or the return, with delta, which is the feedback from our critic. Now, the good thing about critic is that it acts like a value function, and a value function is less noisy and more robust than rewards. Rewards can come up in any moment with a lot of variability, but a value function, a well-trained value function, is usually more stable and more reliable than the rewards that we got from our environment. And that's the secret behind their success. Now, this is a very simple actor critic algorithm. You can do a lot of modifications and add a lot of stuff to it. And this is just a small summary of some of the advancements in recent years on actor critic algorithms. One advancement, one modification that we can do is to make it multi-process. So different copies of the same agent, it's a multi-process activity, same agent play the same game and push their updates to a central network. So the central network is like a hive mind sitting there sending out its agents to the same environment, and they play that environment and they collect a lot of trajectories. And then the central agent either decides to update itself, or each one of those copies are allowed to come in and update the central network. And the way this is done actually determines the type of algorithm you're dealing with. If the network is in charge of training, we're talking about A2C algorithms called uh, advantage actor critic. If each agent is allowed to update the network itself, it's called asynchronous actor critic algorithm. And also Impala. So remember that in Alpha Star, they use Impala, which is a derivative algorithm of this class of algorithms. The other thing that we can do is to limit the policy update, and this actually helps the agent learning process. It doesn't allow it to deviate from the path of the optimal policy. And this idea was first tested on TRPO, trust region policy optimization algorithm, and later PPO. PPO is also incredibly successful. DeepMind used it in many of its recent successes. The other thing is to reduce the bias in the critic. So notice the bias that we used in our previous algorithm here. So this is the TD that we used. This is one step, right? So we go one step forward and update this thing. So we can make it more than one step. We can make it 4-step or 5-step or even more. So we can see that this is this exact same delta, but instead of just bootstrapping after one step, we observe more rewards, and then we bootstrap after that. No, this turns out to be a very it actually helps the algorithm to get rid of unnecessary bias, and it's kind of finding the middle ground between Monte Carlo algorithms and a kind of purely TD bootstrapping method. There's another method called GAE, or generalized advantage estimator, which kind of combines all of these deltas. This is also related to the n-step method, and in many algorithms, such as PPO and TRPO, they're using GAE as their critic. And the final advancement is using deterministic policies with Q functions as the critic and experience replay buffer, like DQN. So this led to the appearance of DDPG, or deterministic deep policy gradient, TD3 and D4PG, which were really successful in continuous action space environments. They also use that for robotics and many other relevant topics. Um, so yeah, in conclusion, deep reinforcement learning has achieved tremendous success in video games and other areas such as robotics by combining the generalization power of neural networks and learning from experience from reinforcement learning. So this is just the beginning. There are still many open questions. And also in our RL journey, we kind of realized that one thing that experience is the key to have a more human-like behavior. So if you want to make more human-like, or if you want to give your agents the ability to understand you, you may want to share some similar experiences with them, and that's the key to give them a human-like behavior. Yeah, thank you guys. Yeah, thank you for attending. So my lecture is officially over. You can ask your questions if you want to.